Good afternoon, ladies and gentlemen. Today we want to take a look at kinetic friction. We're getting into friction now. All the problems we've done up until this point left out friction. It made it a little bit easier, but today and throughout next week we're going to want to add friction back in. The closer we can get to real situations, the more valuable our problems that we're doing will be. And friction, unfortunately, is one force that is present sort of in the real world. So friction is a contact force. So friction only occurs when two objects are touching each other, and it is a force that opposes the sliding of two surfaces past one another. So if we have a box that's moving to the right, then friction points to the left. So if this is the movement that moves to the right, then our force of friction, or capital F subscript FR, points in the opposite direction. It's not always up or down or left or right. It just depends on whatever direction movement is occurring, and then it's the opposite way. It prevents movement and tries to stop movement. We refer to the frictional force as static friction when objects are not sliding past each other. So, as you probably have experienced, you need some amount of force to just get something moving at a constant velocity. That is due to static friction. We're going to talk about that on Monday. Today we just want to look at kinetic friction, and that occurs when the objects are moving past each other. So that is the friction of your tires on your car against the ground. It's the friction of your hand as you try to slide it along your desk. So the force of kinetic friction is equal to the normal force, capital N sometimes, or F sub N, and that is, it's the normal force multiplied by the coefficient of friction. That is this mu with a subscript k. Now we'll see two of those. Mu subscript k is the coefficient of kinetic friction, and on Monday we will see mu sub s, the coefficient of static friction. This is a unitless number. It doesn't have meters per second or any unit with it, and it depends on the surfaces that are involved. So two pieces of wood have a different coefficient of friction than two pieces of ice, or even a piece of ice and a piece of wood. These can only be determined experimentally. We actually have to do experiments, get some data, and calculate the coefficient of kinetic friction. We can't just math it out of nowhere. Scientists actually had to go and do experiments and calculate all of this, all of these different coefficients of friction, and now we have, I imagine there are pages and pages and pages of just coefficients of friction, both kinetic and static. So we want to actually do some of the same stuff we've been doing prior to now, but we just want to incorporate this force of kinetic friction. Remember, it's mu k, or mu subscript k, times the normal force. So our problems are still going to involve net force equals ma. That's not going away now or ever. And it's also going to include this force of friction equals the coefficient of friction times the normal force. So in other words, these problems are pretty much the same as before, like I said just a minute ago. You're going to identify your forces with a free body diagram, and then we are going to use Newton's second law. It's no different skills, it's just tacking on a little extra piece there. So I want to take a look at this problem here. Excuse me. Go ahead and scroll down a little bit for you. A 4 kilogram mass is being pulled across a rough surface. If you see rough surface, that's one of those sort of key words that friction is occurring. When we say smooth surface, that's sort of a clue that there's no friction. And it's being pulled by the tension in a horizontal string, so we know we have some tension. The coefficient of friction is 0.25, and the acceleration of the mass is 3 meters per second squared. We want to find the tension in the string. So I'm going to start with a free body diagram right over in this section. So we've got a box on a surface, and it's got this string. So the string pulling it to the right is the tension. I'll just go ahead and label it now. Because this box is presumably on Earth, it has some weight, mg. It has weight, mg, remember that points straight down, and perpendicular to the surface that it's sitting on is my normal force. So the question, if I remember correctly, says that the object is being accelerated to the right. It's being pulled across a rough surface, and it had the arrow to the right, so I'm going to assume that means to the right. So my force of friction has got to be to the left. Remember, friction opposes motion. It tries to prevent it. So my force of friction is to the left. Now at this point I've got all of my forces drawn, but I want to do a little bit more. It said that my object was 4 kilograms. So I'm going to label it here. I'm going to do some more stuff here. Since I now have my mass and I know gravity on Earth is 10, I can say that this downward force is 40 newtons. I can also say that my normal force is going to be 40 newtons. This box is not accelerating up off the table. It's not accelerating down into the table. It's only moving horizontally. So that means my normal force and my weight have to balance each other out. If we've got a balanced force in that y direction, that means the acceleration is 0, which is what we want. So my normal force is also going to be 40 newtons. Pardon my bad, awful handwriting. Try to fix that a little bit. There we go. So I've got a little bit more information than just what the question told me. So down here, I'm going to use Newton's second law in the y direction to find that normal force. That's what I just did, but I'll do some of the work out. So net force equals ma. And again, we know our acceleration has to be 0. Our box in the y direction is not being accelerated. It's not going into the table. It's not going out of the table. So whatever that mass is, it doesn't matter. It's still equal to 0. On the other side, the sum of my forces, that's going to be my normal force and my weight subtracting each other. And we're going to pretend that I don't know my normal force yet. I know my weight is 40, that mg minus my normal force, and again, the normal force does in fact mathematically and reasoningly equal 4. So from here we want to go into the x direction now. We're really worried about the tension, and there's a little typo here. Instead of finding the acceleration, we are going to find the tension. And because tension is in the x direction, we now need a Newton's second law equation for the x direction. So we are going to use substitution with the equation and the kinetic friction here. So again, we start off with net force equals ma. And my net force this time is going to be my tension minus my force of friction. So that's the sum of my forces. Tension minus the force of friction, because I made to the right positive. My mass is still 4, and my acceleration up above, it told me, was 3 meters per second. Drop that in there as well. So my tension I don't know, but I can do a little bit of substituting in for the force of friction. That equation from the last slide told us that the force of friction was mu k times the normal force. And that is going to equal 12. Just clean that up a little bit. Try to. So mu k times the normal force is my kinetic friction. I actually know both of those numbers. I solved for my normal force before, so that was 40. And that's still equal to 12. And my coefficient of kinetic friction, it says, was 0.25. So I can substitute that in as well. 0.25 times 40. So now we've got an equation we can work with. There's only one variable. It's the one we're looking for. So that helps out. T minus 10 equals 12. So T equals 22 newtons. The only difference in these problems versus the ones we've done before is the fact that we're including now another force. And it's not like we haven't dealt with forces in both directions before. When we had the pulley problems with the inclined planes, we had the tension going up and the mg sine theta pointing down the ramp. So we've done these same sort of problems. The only difference, the only sort of new thing is that we have to be able to take this force of friction and substitute in mu sub k times the normal force for it. Then it's just substituting and solving. So there's nothing too crazy there. Do have another one where it is maybe a little bit more crazy. Not too much though. This time we have an angled tension. And again, we've seen problems like this before, but just never with friction present. So this time we have a 5 kilogram mass being pulled across a horizontal surface, a rough surface where friction is present, by a 20 Newton tension, and our angle is 37 degrees. Coefficient of friction, and we are looking to find the acceleration this time. So again, free body diagram we're going to start with, as always. Free body diagram on this mass, we've got some normal force. Got a normal force pointing upward. Sorry, that's not connected quite right. So we've got our normal force. This arrow is representing our string, so that is our tension. And remember, for our free body diagrams, we don't want to break it into its pieces yet. We can draw our own diagram with those on it, but as far as a free body diagram for a test question or for the AP test, they don't want to see that. That's points off. We also have our weight, our mg, and again, because the string is pulling us to the right, we assume that our coefficient of friction is to the left. So there's our free body diagram. Again, it's not too much different than the ones we've seen before, so fear not. And we're going to do the same process. We're going to take and use Newton's second law in the y direction to find the normal force. Now here's where we need to break this vector down into its components. So we need this angle to be 37. And I'm just going to draw on this diagram instead of trying to fit another one in there. We've got a 37-degree angle, which means that this y component is going to be t sine 37. And this x component is going to be t cosine 37. And unfortunately, as I'm doing this, I did not bring my calculator with me, so I'm going to leave the cosine 37s as they are and the sine 37s. I believe they're about 0.8 for the cosine and 0.6 for the sine, but I'm not quite sure, and I don't want to tell you the wrong thing. So I'll leave those in, and you can solve those yourself in your calculator as you have them handy. So as we're looking in the y direction, the only forces we have is our normal force, our t sine 37, and our weight. So let's go ahead and set up a net force equation for that. So again, net force equals ma. Net force is upward. We've got the normal force and t sine 37. So force normal is positive, and our t sine 37 is positive, and our weight is negative, mg, and that is equal to the mass times the acceleration of the object. Now I'm going to go back up into my problem and see what I have going on as far as variables that it's given me. I've got 5 kilograms, so that's my mass, and I've got a 20 Newton tension. So my tension is 20 newtons, so 20 sine 37. Again, I think that should be about 12, so I'm going to go with that. Again, I'm not quite sure. And that was a 5 kilogram mass? Yeah. Let's work back down here. 5 kilograms times 10 for the acceleration due to gravity is 50 times 5a. And my normal force is still unknown. That's what I'm actually looking for. We also know our acceleration, and it is 0 because we're not moving up or down. This all gets canceled out. Unfortunately, my eraser function is not working very well, so I'll just scratch it out. And it's all equal to 0. We substituted in a 0 for a, multiplied by 5. It's still 0. So again, I believe this sine 37 times 20 is 12 minus 50 plus my normal force. That equals 0, so when we math that around, we get a normal force of 38 newtons. So now that we have our normal force, we can work with our friction. Unless we have a normal force, friction is still a mystery to us. We need the normal force first. Now that we have it, let's go ahead and set up a free body, or I'm sorry, not free body diagram, a net force equation for the x direction. So net force equals ma, and my handwriting is getting progressively worse. Forces in the x direction, we've got T cosine 37 in the positive and the force of friction in the negative. So T cosine 37 minus the force of friction, and that equals our mass times our acceleration. So tension again was 20, and I believe cosine of 37 is 0.8, so that should be about 16. It might not be quite right, but I'm going to go with it. Our force of friction is, again, the coefficient of friction, coefficient of kinetic friction, times our normal force, and that is equal to my mass. It was 5 kilograms. Yeah, 5 kilogram mass. And I don't know my acceleration, but I do know these two. Let me go and substitute those in. I've got 16 minus, let's see, 0.3. Coefficient of kinetic friction was 0.3. And my normal force I found to be 38, so that should be about 12.6. That's equal to 5a. We're looking at 3.4 over 5 equals a. Again, I am calculatorless, but that should be about, let's see, 0.6, 0.7-ish, somewhere between 0.6 and 0.7, a little less than 0.7, about 0.68, I believe. But again, we're doing the same stuff. We're not doing anything different, except we're just adding in the force of friction here. Just remember that it is the coefficient of friction times the normal force. Make sure you find the normal force before you try to do anything else. Last one, it's the same type of problem. If you're feeling comfortable, you're getting this, go ahead and click out of the video if you want. Start working on, I believe it's worksheet number 8, 7 or 8, whatever the next worksheet is. Not quite sure. But we can also do it with coupled masses and pulleys. So I'll just run through this one. I won't give too much description of what I'm doing. It sort of lays out everything for us here. I'll just talk real briefly. Free body diagrams, I'm assuming everybody can do them on their own. But up here we've got the normal force, and below we've got the weight. Those two are going to be equal because this box is not accelerating up or down. We've got friction, and we've got tension here, and tension there. And the weight. So I got my free body diagrams done. Sign convention, like to do it as counterclockwise being positive, just the way I like it. Newton's second law in the y direction so that I can find my net force, or I'm sorry, my normal force for that 4 kilogram block. Let me zoom in so I can have a little bit more space. And let's see, my mass of that is 4. So I've got net force equals ma. A is 0 because it's not accelerating up off the table at all. So I've got 40 minus the normal force, which means my normal force is 40 newtons. Not too bad. And let's see, so we got our normal force, and it's asking us for the acceleration of the masses and the tension in the springs. I'm going to start with the acceleration, and I'm going to use the entire system to do this. So that means that I get to leave out my tensions, and I know my normal force and my weight cancel out. They're balanced, so I don't have to worry about them. The only forces I have that are acting to move these objects are going to be my weight of this second box, the 6 kilogram box, this guy right here, and the force of friction trying to stop it. So those are my two forces. Again, I'm going to write net force equals ma. and I've got my weight, and that was a 6 kilogram box. So my weight is 60 minus my force of friction, which is my normal force, times the coefficient of friction, and that is my mass, 6, plus the 4. Remember, I'm doing this for the entire system, so I need the entire mass of the system. So that is 10 times whatever the acceleration is. Up above, we've got a coefficient of friction of 0.22 times 40, so that is going to be about a fifth of it. We're looking at 8, maybe a little less, somewhere around 7.4, I'm going to call it. Might be 7.2. Minus 60 over here, and that is 10A. 7.4 off of 60 is going to be 52.6. That equals 10A, which means our acceleration is 5.26 meters per second squared. That math in the middle might not be quite right, don't trust me. But it should be around that area. Double check in your calculators as you're doing this. But otherwise, again, this is not anything too different than what we've done before. If you feel good about the quiz and doing this, then adding the friction on is not that big of a deal. On Monday, we'll have another little video for you to go over since I'm going to be gone. And that will deal with static friction, where we're having friction before the object's actually moving. And that gets a little more involved because we have to decide, well, is the box going to move? And then we decide which force of friction is going to act upon it. But the video will be there to guide you through it, and we're not stopping there. Of course, I'll be back on Tuesday, and we can clean up any of this, both regular friction, both kinetic friction and static friction. We can talk over on Tuesday. So again, thanks for listening. And if this was something that you think would be helpful in the future, if we got onto a subject that you really didn't quite get during class, and you think these videos would be, or more videos like this would be good to have access to at home, just let me know. I'm willing to try this out a little bit if I think a lot of people would benefit from it. And I could at least test drive it, see how many people are actually viewing it as those videos go up. But if this is something you liked having this, and you think it would be awesome to have this maybe at home after school or on the weekends while you're studying, to hear my wonderful voice, which I'm sure you're very enthused for, let me know, and I'd be willing to give this sort of more of a pilot, more of a test drive. This was sort of a last-ditch effort to try to get something done today, Friday. But yeah, I'd be willing to do it more often if people are interested. Just let me know. Thanks. Have a great day. If you have any questions, just ask. Even though people might be taking tests, call me over, raise your hand, ask a question. Have a good one, folks.